All right. Great start. Anyway, all right. Thanks for the intro. Yeah, let me launch right into it. I'm not going to read the abstract. Real quickly. So I work for CosmiQ, which is a lab that's part of In-Q-Tel. In-Q-Tel is a strategic investor for the government, but our labs are specifically open source. The CosmiQ labs focuses on geospatial. So we've had a number of recent efforts. SpaceNet's obviously what I'll be talking about here. We've had a few other ones. I won't go into the detail, but certainly if people are interested, go ahead and look those up. So what is SpaceNet? So SpaceNet is a nonprofit LLC that we manage. And the idea, right, that as you might have figured out, right, the name is modeled off of ImageNet, right, which is this very successful computer vision competition that ran for quite a while, and really helped advance state-of-the-art kind of in standard, cell phone type images. But as you all know, right, there's still in a lot of ways a lack of data for advanced models for the geospatial domain. So something we kicked off a few years ago, trying to help alleviate that. We focused on foundational mapping for this effort for a number of reasons. One being it's easy to open source that data, and the connection to things like disaster response is very, very obvious. We have a number of partners. Most of the imageries come from Maxar, but we also had imagery from Capella Space, which is in this case synthetic aperture radar. We recently had data from Planet as well, and then a number of partners, both in industry and in the government. So the NGA is actually a formal partner to SpaceNet. So the motivation here, I don't think I probably need to spend too much time here. I think this group has accepted this, right? So after Hurricane Maria, it was a very, very impressive and laudable effort to remap Puerto Rico, given all the devastation. And it took an army of mappers, or 5,000 people, over 2 months to remap the buildings and the roads. And again, this is a great effort, but if you could just accelerate this with machine learning, that would obviously be very helpful. Something that wouldn't take, something that went from 2+ months to maybe a few hours would obviously be very helpful. So in our mind, there's kind of 4 pillars to what makes a useful effort in terms of what we're focusing on. And the first, the primary one, right, is labeled data sets, right? So we need good labeled data to build these machine learning models. And so that was the first place we started. So what we've done over the last 4 years, we collected imagery over 400 areas, lots of building footprints, millions of them, roads, and then a pretty large area of satellite imagery. And then to really drive interest, right, in these labeled data sets and see what can be done, run public data science prize challenges. So there's actually 7 challenges now, 7 just wrapped up this last week, and distributed prizes for each of those. And then the algorithms from those challenges have been open source. So that's, I think, pretty crucial. There's obviously been other remote sensing challenges to date. We fully acknowledge this, and something that I think is really important. One thing that's been pretty exciting for us, though, is we've been able to open source the algorithms, all the top 5 for each challenge, and I've been seeing a lot of interest in that. And then we've spent a lot of time on evaluation. So instead of just kind of ending the challenge, we've put a lot of effort into analyzing the results. And then there's some key characteristics for open data sets, right? I won't focus on this too much, but you need high quality. You need it to be available, right? If your data is only available during a challenge and afterwards, or it's got a license that really restricts use, it's not that useful. And so been a lot of effort on our part and our partners to get this Creative Commons license that's actually also commercially available, useful. So we actually have companies that can use data and they're not worried about being sued about infringing on license terms, making sure it's accessible. So AWS has been a partner, and they've stored it on the cloud for free. So that's really nice. People can download it at will whenever they want, and making sure it's interoperable with other standards is important as well. So kind of what's the data look like? So as I mentioned earlier, right, Maxar has been the primary source of data. And so in this case, these are the locations for that data. And the top or the bottom right actually is EO plus SAR. And then the bottom left is an Off-Nadir challenge. And I'll get into those a little more in detail going forward. And then the most recent challenge, SpaceNet 7, which is just finishing up now, is medium resolution. So this is planet imagery at 4 meters versus the 30 centimeter or 50 centimeter of Maxar. And this is a lot more locations, right? So in this case, 100 plus locations all around the globe. And here you can see where we have that data set. So of course there's the imagery, but then labels are equally or even more important in a lot of ways. And so we've had, the building footprints for the high res data, about a million-ish buildings, million-ish labels at this point. And then in the middle there, we have building footprints also for the planet imagery, and that's actually 10 million plus building labels. And then also roads, right? So kind of the two most obvious things you could do foundational mapping, right, are buildings and roads. So we've looked at both of those. Specifically for the roads, it's been the road network, not just pixels. Just a few stats. I don't need to actually go into this too much detail, but again, the cities and the labels for the roads and the buildings. So then the challenges, right? This has been so much of the effort of the SpaceNet initiative is to run these public challenges. And we've really tried to take an iterative approach. So start with SpaceNet 1, which was just one city, in this case, Rio de Janeiro, and look at building footprints. So, the actual polygons, not just a pixel mask or bounding boxes, but the precise polygons. And this anecdote that makes me chuckle, and I don't think it'll surprise anyone on this call, but when we first set this up, one of the original partners, who was not a geospatial expert, was convinced that we would need a tiebreaker because they thought everyone was going to get a score of 99 out of 100 pulling out building footprints in Rio, and the winning score for SpaceNet 1 was about a 22 out of 100, right? So still a challenging task, which again I don't think surprises anyone here, but I think the general computer vision community views this as almost a solved problem, whereas clearly is not even close to solved given all the challenges with overhead imagery. So SpaceNet 2 kind of built upon SpaceNet 1, still looking at building footprints, but in this case, 4 different cities. So looking at geographic diversity and how scores vary between cities. SpaceNet 3 took a leap to looking at roads. So in this case, actually road networks, right? Not just the pixels, but actually trying to build a routable network in those 4 different cities. SpaceNet 2. So again, Vegas, Paris, Khartoum, and Shanghai is a pretty diverse field there. SpaceNet 4, was another bit of a leap. That was pretty exciting. This was a unique collect taken over Atlanta as the satellite passed overhead. So it was 27 different collects from different angles, all the way from about -45 to +45 degrees. And that's this GIF in the middle. You can see the Brave Stadium as the satellite passes overhead. So trying to look at how building footprint extraction performance varies according to nadir angle. SpaceNet 5 went back to roads again. In this case, we're looking at travel time. So not just the road network, but an estimate for what is the travel time for each segment of the road in those different areas. And then we had another nuance, which was we score on an unseen city. So the test was, can your model generalize to unseen areas? SpaceNet 6 was the first time we dabbled in non-EO. So we actually had SAR data as well as electro-optical over Rotterdam for SpaceNet 6. And SpaceNet 7 is the most recent. This is the first one we're looking at the time dimension for the first time. So 24 months of collects over 100 different geographies, looking at areas where there's a lot of construction. So looking at the GIF on the right shows a construction of buildings in one of those areas of interest. I'll kind of blaze through this, but there's been a lot of progression, quite a bit of traction in terms of downloads and partners joining for SpaceNet. Real quickly, to support SpaceNet, we built this Solaris package, which just is trying to help ease the burden of entry for getting started in geospatial data. I think this is it's been helpful for more some competitors to use this package. Note on just kind of uptake, almost over 800 terabytes of downloads at this point, and a lot of participation internationally in the challenges. Actually, all the winners in the most recent challenge were all international. So I'll go through now briefly some of the results from the various SpaceNets, and I'll kind of I'll do this quickly because there's 7 different challenges to cover, and I want to give some time at the end for questions, but hopefully some of this is compelling to those on the line. So SpaceNets 1 and 2, right, were both building footprints, and SpaceNet 1 actually, you know, 2016 is still not that long ago, but the winner didn't even use a deep learning method. And then kind of, you know, later on we got more traction, kind of higher quality submissions, and we saw a pretty good boost in performance for SpaceNet 2. What we're showing here on the right for the imagery is performance in different cities. So top left of this right image is Las Vegas, whereas bottom right is Khartoum, and unsurprisingly, right, Las Vegas is much easier for building footprint extraction than Khartoum for a host of regions, but again, that was kind of interesting to quantify that. So what we've noted is, you know, an uptick in performance. Not too surprising, right? Algorithmic advances over the years. So SpaceNet 1, we had a score of about 0.25 or so. SpaceNet 2, that jumped up significantly. SpaceNet 4, we saw another boost. So this is a very encouraging trend here, and again, surprised at the level of increase here over those even couple of years. So I'll focus kind of on the most recent SpaceNets to provide a little more detail. So I'll start with SpaceNet 4, which is again this Off-Nadir challenge, and so a little bit more details on the data set. So I kind of mentioned this already in terms of the imagery. 27 collects over Atlanta at 0.5 meter resolution, quite a few labels, and you know, as always for the challenge, we open source the solutions at the conclusion of the challenge. So why Off-Nadir, right? Again, I think I can skip a lot of this motivation for this audience, but I won't in this case. But you know, after a disaster, right, the first image is often highly off-nadir. The problem is most algorithms are only really trained for nadir imagery, and so knowing how well you can actually extract, in this case, building footprints at off-nadir is pretty important if you really have a timely scenario. And of course, there's difficulty here, right? So there's variable shadows when you're looking at off-nadir. So the top left pair there is looking from the north versus the south, and you can see very different shadows depending on what your viewpoint is. If you're looking with or against the sun. There's footprint displacement, right? Just caused by different angles. Obviously, massive occlusion if you have skyscrapers in a dense urban area. And then just based on geometry, right? You have degradation of resolution. So if you're looking at highly off-nadir, your resolution is going from from 0.5 at nadir to 1.3 or something highly off-nadir. So a very big shift in resolution. For building footprint extraction, we've used a similar metric for all SpaceNets, which is looking at the intersection over union of the ground truth and proposals. We usually set a IU threshold of 0.5 or greater. This is pretty standard for normal situations in computer vision. So we're just doing a little schematic here of ground truth in blue and then proposals in red, and showing what what kind of precision you need for a building footprint to get this 0.5. And obviously this is it's a threshold, right? So you can tune this depending on your desires. 0.5, I think, is a good compromise we've seen, being too stringent and really too lackadaisical. And we compute the F1 score based on true, false, positives, and negatives for the total score. So how did it do for SpaceNet 4, looking at off-Nadir buildings? At Nadir, the winning algorithms found 8 of every 10 buildings, which is pretty impressive. Although only found 6 of every 10 buildings in very off-Nadir, so a big shift in performance, and also a difference in false positives. And to illustrate this a little more concretely, here this plot is showing the SpaceNet score. So again, this is F1 of building extraction on the y-axis, and then the x-axis is the look angle for degrees. So we see pretty close clustering here, scores to the top 5, and scores of above 0.8 at Nadir, which degrades significantly as you get above about 35 degrees. This is much harder than to pull out buildings footprints accurately. Also, it's the sawtooth pattern, which was caused by north versus south facing buildings and the difference in shadows. So I'll blaze on to SpaceNet 5 at this point. And this one was looking at roads, right? So the rapid extraction of road networks and key routes is critical in dynamic scenarios. It's a disaster response. Excuse me for a second. It's nap time. And there's options for this, right? There's commercial and open source approaches. These are often manually intensive. As we talked about earlier with needing to remap Puerto Rico after Hurricane Maria. Commercial solutions, right? The solutions and data are often proprietary. They're often incomplete, and they're often outdated. For example, right, the top right is OpenStreetMap. It's a great resource, obviously one that is very foundational to a lot of the things that have been done in geospatial, but it's unsurprisingly it's incomplete, right? So you see in this case roads going through the buildings, so it's not perfect. So there's room for improvement. There's academic approaches. There's been an increasing amount of effort looking at road extraction in academia. Often these just return segmentation masks, which is a great first start, but it really doesn't help you actually do any routing. It's just pixels. And even if you do get geometry, the actual road network, road properties are not often included in these works. But road properties are actually crucial for true optimized routing. And so, here's just a toy example of a road network. And on the left is just doing distance based navigation, right? Which is what you get typically from these, the current outputs from academia, or just pixels. But if you do time-based routing, you get the rightmost plot here. So it's a very different route, and obviously it's very important in many scenarios, right, to do time-based routing. Is what we usually care about versus the shortest distance. So knowing the speed estimate of each roadway and the travel time it's important to do this real optimized routing. So SpaceNet 5 aimed to tackle this, and so we had features labeled for the roads. One thing I bet I skimmed over earlier is in SpaceNet, all of these labels are human annotated. So these are all hand drawn and checked and verified. And so pretty high quality labels here. Lets us get a road speed estimate based on the road properties. And so the goal is to build a challenge that focuses on automated road network extraction and optimal routing using travel time projections. So just another note of why this is important. So here's a snapshot on the right of OpenStreetMap over Shanghai, which is one of the SpaceNet cities. And it's colored by the max speed tag. And as you can see, right, this is primarily blue. So most of these roads have no max speed estimate. So this is something that's hard to do, again, with kind of open source solutions that currently exist. And this is another note on just kind of the current state of the art for many approaches, which is segmentation, which has seen great results in some sense, because the evaluation metrics are usually like a F1 score or relaxed F1, and you can get very good scores. So the middle example here has a 0.92 F1 for road extraction, one of the recent papers. So that's great, but it doesn't really capture what you want. So here's a toy example that we kind of came up with a bit ago when we were trying to figure out how to run SpaceNet, actually 3 and 5, which is on the left is a ground truth of a small no-road network. In the middle and the right are proposals. So the middle, obviously the road widths are incorrect. So you get an F1 score of 0.82. On the right, you actually have a higher F1 score because your road widths are correct. The problem is obviously you have this big gap. And so, most of these pixel-based metrics would actually incentivize the proposal on the right over the middle one. Obviously, the problem here is, right, this proposal on the right is terrible if you want to do routing because you have gaps in the road. So this kind of led us to actually develop a new metric that actually measures what we want, which is actually routing. So the apples metric, which is average path length similarity, actually measures the difference in route lengths between nodes of interest and sums those up and gives you a score between 0 and 1. There's a lot of features here. I won't focus on it. I can come back to this later if people really want. But again, what we're trying to measure is actually the routing efficacy of the proposal versus the ground truth. So the output of SpaceNet 5, actually the baseline model did very well for SpaceNet 5. You'll see here, this plot on the right shows the Apple score versus inference rate. And the winning algorithms did improve in Apple's over the baseline, but only by a few percentage points, and were also much slower. So for some of the examples, we'll focus on this baseline algorithm. Just another note, which is comparing SpaceNet to OpenStreetMap. Again, this is by no means meant to denigrate OpenStreetMap, but what we find here is training models on the same imagery, same architectures for the model, but using SpaceNet labels versus OSM labels, we see a marked increase in score if we use SpaceNet labels. And so this, I think, just down to just maybe a little higher precision labels. The registration between labels and imagery is greater for SpaceNet versus OpenStreetMap. So you get this nice performance boost if you use these higher fidelity labels when you're trying to pull out roads. So just a note on the baseline model, we call it CRESI. The approach here is take an input image tile, run it through a multi-class segmentation model, refine the aggregate model. This is the top right little inset here to get out a network, which gives you a road graph, which is the far left inset image. And then you can use the multi-channel nature of your segmentation model to pull out an estimate for road speed for each road segment, which of course then you can get travel time based on the distance and this road speed. So we get road speed for each one. We also have to scale to large areas. Obviously, if you just do small chips, not important, not interesting. So this is how we do that. Pretty simple approach to do that. And so how does this actually work in practice? So here's the baseline model applied to a new unseen city that we haven't tested or we haven't trained on at all. This is Dar es Salaam. So here's the input image. Here's your first step of your segmentation mask for roads. Here's your pulled out network. And then here's colored by road speed estimates, right? So yellow is slower, red is faster in this case. And here's that same road network overlaid on the imagery. So of course, not perfect, but it's doing a pretty good job here of pulling out road networks in a totally unseen geography, something you can actually use to route on, right? So comparing this to previous research, so road tracers, a pretty well publicized effort to pull out road networks, and we see a significant improvement over that method with this CRESI. So here's just a snapshot of the same test area for the left road tracer, and then right is CRESI. We also have very high fidelity travel time extraction. So the errors in road extraction is typically actually the geography, not the speed. Geography is actually a lot harder. The geometry is much harder. Once you get geometry, speed's easier. Here's just a GIF of Las Vegas. We're building up the road network from yellow slow to red faster. So again, Las Vegas, like buildings, roads is easier. So we're doing a really good job here of actually building this road network in Las Vegas. And of course, the last thing, right? Well, the original motivation of this for roads is doing optimized routing. And so here's an example on the left, right? This is your just road network, where the only information you have for each segment for the road is distance. And here's the route you take from point A to point B. And on the right is, okay, let's actually pull out the estimate for road speed with this method, and then let's reroute. And so obviously you can see a very different route would be taken in the two cases here. If we're actually looking at actually optimized time, this is why pulling out this road travel time is important. I won't go into this in too much detail, but kind of surprisingly for us, so remember Dar es Salaam was a city that no one trained upon. It was totally new geography. And the overall scores for both the baseline and all the top 5 competitors didn't see a marked decrease in score between the cities they could train on and this new geography. So these models do really seem to transfer pretty well. They seem fairly robust in this case. When you have, we had 6 training cities across the globe, and then it seems to work pretty well on a totally unseen geography. And of course, since this scales, you could do this, you could pull out like the entire city of Khartoum road network in just a few hours with a pretty, just like a BV laptop. And that's what we're showing here on the left is pulling out Khartoum, and the blue here is the actual road segments that we extracted. All right, so let me detail SpaceNet 6 briefly. This was the first challenge where we actually were looking at non-electro-optical data. So we had aerial SAR as well as optical from WorldView 2. So on the right here is just some of the strips, observation strips over the port of Rotterdam for the SAR collect. So a little bit detail on the data set. We had multiple collections, 204 image strips actually from this aerial platform. And so as many of you probably know, right, Capella is a startup. Its goal is to build SAR satellites. So this was a aerial collect with designed to emulate what they're actually going to have up in space. They actually have satellites up now that they're testing. And so actually pretty good data set, X-band, quad pole, space resolution of 0.5 meters. So this is pretty exciting, at least for us it was. And then we had also, along with the SAR data, Maxar optical data. So this is not completely concurrent, but it's within a few days. So things like infrastructure would not change. Obviously, things like vehicles would change. And so then we can overlay those and see obviously same regions, but significant difference in appearance between SAR and EO as expected. For the way we formulated the challenge is for training, we gave competitors SAR and optical to see if they could improve model performance by having both of those modalities. But for the test, we only gave them SAR. So the rationale here was, this would emulate perhaps many scenarios where you might be able to train on all various types of data, but maybe in the actual deployment scenario, all you have is SAR because of cloud cover or other issues. For the data set, this was a case where we actually, for once, didn't have to make our own labels. This is something that one of the ministries of the Netherlands actually has a great labeled data set over Rotterdam we could leverage, and it actually has a LiDAR to get a building height estimate as well. So it's something that people could use to perhaps boost their models. And it's about 50,000 buildings in the final data set, with some label curation and improvement manually by the team, just to make sure everything was in good shape. So kind of as usual, right, there's a baseline model that the CosmiQ team puts together for SpaceNet. In this case, we use both optical and SAR, and try to build a segmentation model and then pull out the building footprints. We've seen in all the recent SpaceNets, people have used a UNet type structure and different encoders. So we use just a VGG11 encoder. We've typically seen competitors use more advanced encoders, like SCNets or ResNets, that are typically a little slower but higher performant. And so this is, again, this general structure is what all competitors took, even though they did find significant improvements upon the baseline model. So here's the winning score. So again, this is the same metric that we used for, say, SpaceNet 4. We're looking at the intersection of a unit of buildings. And the takeaway here is maybe not exactly what the overall score is, but the improvement over the baseline was exciting for us. So we had this baseline that was about 24, and then the winning score was 42. So this is doing a decent job. Right? This is out of 100. So it means an F1 score of 0.42, pulling out buildings from SAR at Off-Nadir. And even it's pretty impressive when you consider a lot of these buildings are decently tall. And SAR is obviously not something that's well understood by the computer vision community. So here's some of the example predictions of the SAR. So the yellow in this case is ground truth, and the green outline is the predictions. And here's just a note, again, I kind of already mentioned this about the approaches people took. So unsurprisingly, most competitors, or all competitors in this case, use an ensemble of models, so multiple models that they then average together to try and improve score, and use different types of UNet encoders within different decoders. So one thing we can study, right? I mentioned that we spend a bit of time looking at the results of the competition, doing analysis. I've stripped out most of this just for the record. In the interest of time, if most of this is going to be something that you can revisit at your leisure if you're interested. But here's one example: is we had these many revisits of this aerial collect. So how much benefit do you get from each of these visits? Let's take a look at that. So this plot on the right is showing the score versus the number of revisits. And this is interesting to know because you'll see, like, okay, we have a rapid increase up to 2 or 3, and then we start to asymptote. So what this would say is, 2 revisits really gives you a huge boost, but doing 8 revisits doesn't really give you anything else. Obviously, data collection is expensive, so things like this I think can really help when you're trying to design both data sets and studies. Here's just a final picture of SpaceNet 6 for the winning model overlaid on the optical. And so again, not perfect, but doing a pretty good job. So again, remember the model here is actually given outputs on SAR, but we just put on optical to aid the observer. Doing a pretty good job of pulling out these building footprints. So let me kind of conclude on SpaceNet 7, and we should have some time for questions still. So SpaceNet 7, right, was a departure where we went from this, very high resolution 0.3 or 0.5 meter imagery to a medium resolution, right? So this is planet imagery. Usually the average is about 4 meter GSD. And we're still trying to pull out building footprints. So this is just a shot where we have the planet image with building footprints overlaid. So there's plenty of motivation here. I'll kind of skim over this, but change detection is a lot of this, right? So that's one of the things that the planet constellation offers, right? It's low resolution spatially, but higher temporally. And so if we can get a time series of data, we maybe can look at change detection, especially if we're looking at vector labels, not just pixel masks. And there's plenty of applications of this, to the UN and other efforts as well. So in a nutshell, we have this deep time stack of imagery covering about 100 different areas. And on the right, you see one of those areas. And you'll see over time, there's a lot of construction going on. So the different AOIs here were selected such that they had significant change. And so that there actually was, change detection is a meaningful thing. It's not just some shadows. There's a lot of construction and building change. This actually was accepted as a NeurIPS competition. So there's a talk in 4 hours and 20 minutes on the results of this. So you guys are actually getting a little bit of a preview in the following slides for some of these results. As NeurIPS is ongoing now, for those who weren't aware. Here's, as you all know, right, the data set's very different from standard imagery, right? So there are video data sets that exist. So the bottom couple snapshots is from MOT 17, whereas the middle row is sequential images from our data set. So much more change going on. And in the building size or object size is actually a huge difference, right? So the top left shows object size in pixels for COCO versus ours. And you'll see, obviously, these images are these objects are very small, just a few pixels often in size. And so this makes it very tricky to actually pull out precise boundaries for these very small objects. To drive that home, this is a very pathological image. This is about the worst I could find. They aren't all quite this bad, but on the left here is a raw image from the Planet Collect, and the right is there's labels overlaid. So actually labeling was done with using both planet imagery and higher resolution images, and kind of laboriously looking for differences. And the takeaway here, one of the takeaways, at least to me, is that I would find it more or less impossible to draw the bounding boxes or the building footprints that are drawn on the right. So it's in a sense super labeled, right? So there's been a lot of talk about weak supervision, right, in computer vision and machine learning in general. We have the opposite, right? This is kind of over labeled, which is a kind of an interesting paradigm. Like I said before, right, it covers all 6 inhabited continents. So a lot of diversity here. And then, here's just a shot of over time on the top right, and then the bottom, the building footprints getting built up. We, as with kind of past challenges like Apple's, we ended up making our metric. We intended to use existing metrics like MOTA, multiple object tracking accuracies was the intended to use, but turns out that doesn't really translate well to this problem. So we ended up making our own. I won't go into too much detail here, but what we end up doing is we're looking again for the overlap between ground truth footprint and proposed footprint. But then we have 2 terms, which is a footprint tracking exercise. So we actually, each building footprint gets assigned a unique identifier, and then we're trying to track that through time. So can you track that through time, which is essentially an address, right? And then also there's a change detection term, which is, do you spot when a building appears correctly? Can you actually identify the correct epoch when a building appears? This is obviously something that's very important to do. 2 terms that give you this SCOT score. Just a real quick note on the baseline model. As you might expect, right, we start with a, look at the top row here, start with an input image, feed it into a segmentation model. You get out a segmentation output, extract the polygons from that, and then I assign identifiers to each of those buildings. And then at a later time, we try and do the same thing, and then actually we propagate those identifiers. So the actual right column here, right, is actual sample output. And as you'll see, if you look at those numbers, right, we're doing a decent job of matching up these building identifiers, which is essentially an address, right? So actually tracking those addresses over time. It's not perfect, of course, but again, this is the general approach that we took. And here's just another snapshot of kind of the same thing overlaid on the actual imagery. And as you'll see, right, if you look on between epochs, the building identifier is not perfect. There's certainly some errors here, but doing a better job than frankly I expected, given the difficulties in pulling out building footprints from this resolution of imagery. And here's just a shot at a larger scale. So here's an input image. Here's the segmentation mask, and here's the actual polygons that are pulled out from that. But even more exciting, right? That's the baseline model. Is the competitors vastly outperformed the baseline model. So the overall score here of the baseline was 17, whereas the winner had a score of 41, and this was pretty shocking to us. Also, was pretty cool looking at runtime, and so the bottom right here is the baseline model. So up and to the right, it's best, right? It's a higher score and faster. And what we saw is the winning submission was far faster than all the runner-up submissions, and nearly as fast as the baseline model, even though it's far more performant. So something really excited to dive into more in the future. Just had a couple more slides, and then I'd love to hear questions. Here's just a snapshot of the predictions, right? So in this case, the blue is a false negative, yellow is a false positive, and white is a true match. So obviously it's not all white here, but there's a lot of white given the resolution. So doing a pretty good job of pulling out footprints. Let me zoom in on an area. Here's your raw imagery that's your input. Here are the ground truth labels for that area. And then here are the predictions. So again, white is a true prediction, whereas blue is a false negative, yellow is a false positive. So obviously not perfect, but at least in my mind, doing a remarkable job of this winning submission to pull out building footprints at this resolution. So let me just conclude real quick. SpaceNet 1 through 7. At this point, it's a pretty good size repository of labeled data that spans the world, and importantly, right, has a permissive license. So it's something that academics can use as well as companies without worry about infringing upon the license. SpaceNet's brought together market competitors. So Maxar, Planet, and Capella, right, are all technically competitors, but they've all joined this consortium and contributed data. So that's been a huge, really exciting for us. There's been academic involvement, right? IEEE has been part of it. We've been really happy to have their support. And NGA, government's even part of it. They're a formal partner as well. We've engaged increasingly talented researchers to solve these difficult problems, right? So one example is the winner of SpaceNet 6, also placed in the COCO competition. I think even cooler is that one of the perennial SpaceNet winners, Salem Seth, winners being top 5. So he's only won, I forget how many he's won, but he's not crushing everything. He certainly didn't win 7 or 6, but he's always in the top 5. He actually won the massive $1 million Facebook deepfake challenge. So the point here being, we've had really, really high quality competitors for SpaceNet. So the outputs of these, I think, really are world class in terms of the algorithmic performance. And then we've actually provided these repositories, right, of these winning submissions on GitHub, and we know they're being used, right? XView is another challenge, right? This geospatial challenge that they actually use SpaceNet code for their baseline, and we've seen uptake from academia. About over 100 papers are using SpaceNet data. So kind of the original goal, 2016, was to try and create something like ImageNet for geospatial data. And I think we've largely been successful. This is a snapshot I took actually in CVPR back in 2017, back when we could go to conferences in person, when Fei Li was talking about what ImageNet had accomplished. And so, even she acknowledged, if you look at top left here, that SpaceNet had actually done some good work there. And we've done a lot since 2017. Everything I've covered actually in this talk has been post 2017. So pretty exciting what we've done there. I'll end there. Plenty of information channels if people want to learn more about this. But yes, thank you for your time, and I'll be happy to take questions if there are any.
Thank you, Adam. It's very interesting presentation. So yeah, if someone has questions, you can unmute yourself and ask, or type your questions in the chat box. Maybe I can start. So I have a quick question. So it looks like the input spatial resolution data is very important for extracting the features. So how do you think what's the spatial resolution do you think is good for that you can extract the output with high confidence?
No, that's a great question. Actually, kind of tangential to all the SpaceNet effort that we obviously detailed here was we've actually done a couple different studies on that exact question of resolution, and it's been more on the vehicle detection side, but I think those lessons translate, and really I think from what we've seen, I'll be real brief in terms of findings, which is objects that are 5-ish pixels in size or greater actually seem to be adequate in a lot of cases. So you don't actually need to be that big. The bigger the better, of course, but it is an asymptoting curve where above 5 pixels seem to be doing pretty well. Below 5 pixels, it really kind of drops off a cliff.
So what's the output, the format? Is vector or raster or both?
So in this case for SpaceNet, we almost always get a raster output as an intermediate step, but then we're scoring on the vector. So we get the actual vector outputs for every single building or road.
So for the road type, is there any road type like highway or street? That kind of label available?
Yeah, so the labels for the roads, the actual ground truth, includes a number of features, right? It's obviously the topology of the road, but then each road vector has a label of road type. This is like highway, secondary street, primary street, etc. Number of lanes, surface type, is it paved, is it unpaved? All these things, and then from those, right, there's an estimate of travel time, or sorry, speed limit, and travel time, obviously giving you the length of the road. So those are all the labels you have. The actual output of the algorithms, you could pick anything, right? Frankly, to pick as your feature, we picked road speed. That's what we thought was the first thing to start with. And I think once you've proven you can do road speed, you could do the exact same approach to pick another feature like paved or unpaved. Anyway, the output algorithms give you the topology as well as the label of the road speed for each road segment.
Thank you. Another question about the data availability. So this can only be downloaded from AWS or?
Yeah, right. I kind of skimmed over that. The data is available on AWS, but it's, again, we've had good luck with this, and it's free to download. So if you're worried about it disappearing, it won't. But also just go and download it. It is all up there, and there's really no barrier at all to get a hold of it.
Yeah, I saw your slides about the spatial coverage of data globally available. So how many cities are available, the data?
Yeah, it's 11 different cities at the high res. So let me see if I can rattle them off. Rio de Janeiro, Paris, Shanghai, Khartoum, Las Vegas, and then we had Mumbai, Dar es Salaam, San Juan, Puerto Rico, Dar es Salaam, Atlanta, and Rotterdam. Those are the high res ones. The planet resolution, right, 4 meter, that's 101 locations. I'm not going to rattle all those off, but there is overlap, which is exciting. There's about half a dozen cities which are in both planet and Maxar imagery. And that those planet images cover all 6 continents, so they're all over the place. I stopped screen share just so I could see the chat. I'm not positive how to see otherwise. And if you go to spacenet.ai, that's got a lot of links to a lot of this data and a lot of the a lot of the actual detailed information is on our Medium blog as well, which is let me just type it in here. It's the downlink.
Okay. Excellent. Is there any other questions? Okay, I think that's all. We appreciate our speaker, Dr. Adam Etten, for his great presentation today, and also thank you all for joining this webinar. We will close our webinar. Thank you.